Hi. Before we talk about mirrors, we need to talk a little bit about what it means to see things. But this guy right here, this is called a plane mirror because it's nice and flat, and we're going to talk about them today. Yay, plane mirrors. This guy right here is convex because it doesn't look like a cave. It's like the other side of a cave, like you'd see from The Rock or something. You can use these often on cars to see an enormous range. See how you can see a whole bunch of my ceiling like that and the camera. And this guy right here is a concave mirror because it looks like a cave. There's a little cavity inside of it. And you see how eventually we can get to a point where you're looking at the camera and you see it really big and then upside down and right side up, and well, that's cool. So I don't know if you can see yourself now, but I hope that was interesting. But before we even talk about plane waves, we need to talk about what it means to see a thing. So let's say that I have a flower and I want to look at the flower with my eye. I have the eye of physics here with some nice physics eyelashes, and I want to look over here at a flower. And the flower, well, let's put the flower here first of all. What does this have to have? 7 or something if I'm doing this side? 4, 5, 6, 7. Prime numbers, flowers, yay. And the flower naturally sits in a flower pot. Here we go. And probably some dirt in there too. But if you see a flower, that means that rays, now remember, rays come straight from the thing to your eye. Rays from this part of the flower are entering your eye. And if they're entering the lens of your eye, then I suppose some cool stuff is going on inside your eye that we'll talk about later in the retina, and you're getting some signal, and there's some lens action going on right here. Then you are able to see every bit of light that comes into the lens of your eye because it's making an image on your retina. That's cool. But doesn't that also mean that if you see this part of the flower at the same time, don't you also have light rays coming into the lens of your eye from right there? Sure you do. Yeah. But don't you also have light rays coming in from the flower pot? Sure you do. And they're all coming in like here, nice and straight, and they're not supposed to be thicker, but they're just, oh man, they are supposed to be straight though. And they're all coming into your eye also. And what if there's something really, really far away from here, like Newton? Hi, Newton. So Newton's over here, and he's all smiling, and he's got that curly British hair thing going on, and he's over here looking like a girl. All right, and so Newton's got some light rays coming from him, but the cool thing about them is they're so far away that when they reach your eye, he's so far away, when they reach your eye, they seem to be parallel. What if there's also a gnat, a little tiny gnat flying right here, and that gnat's like wing and wing, and light is coming from the gnat, but that light is going like this, that, and that. And you see that these light rays from the gnat are spreading out. So this is close, and I'm going to say lots of divergence. Those rays are spreading out from each other a lot because something that's close has a lot of divergence, and Newton is far away, so it has little divergence. Little divergence is the same thing as sort of saying almost parallel. So as we go on in our study of light, I want you to remember that things that have a great divergence appear to be very close, and things that have almost parallel light rays seem to be very far away. If you look at things that are far away, they don't take up a lot of your field of view. That's actually why they're hard to see. Take a break from the computer, look away, and look at something far away from you. It's hard to see because it's not taking up a lot of your field of view, which means a very small fraction of your retina back here. You know your eye is an eyeball, and you got retina business right back here. Each of these things is forming an image on your retina, and the gnat's image on your retina is actually bigger than Newton's image on your retina if Newton is a great deal away, and the gnat is relatively close. So you get, well, it's like precision and accuracy inside of here. If you've got a relatively big image of the gnat forming back here on your retina, then you can see it very well, and that's because the rays are greatly divergent. So solidify that, and we'll talk about it a little bit more time later. But the next thing I want to point out before we actually go into mirrors, look at all this stuff we have to do before mirrors at all. Notice that it's almost as if the way I've drawn this, it seems to be each of these things is just zapping light at my eye. That's a little bit silly, right? So let me fill in what's actually happening. The sun is shining. Yay! And it's looking pretty cool. It's a happy sun up here. And the sunlight is hitting the flower. And what's happening here? Specular reflection or diffuse reflection? Well, the very fact that I can move to different angles and still see the flower in the sunlight shows that it's not specular reflection, but rather diffuse reflection. So light is coming from the sun and hitting the flower, and it's reflecting in all directions. So that means if a ray of light hits this flower right here, not only do rays of light come at my eye, but they also go absolutely everywhere else. And this is in 3 dimensions. The light is coming away from that particular spot. Also this spot. And oh, this picture is going to get rather complicated. I want to try to indicate to you, wait a second, every part of this flower is reflecting light in every direction. This is why we only pick a few light rays to draw, because this is insane. Look at that. That's a mess. You can't study that diagram. So what I'm gonna do is I'm gonna pick just a few select light rays, but I don't want you to forget, because I had an inclination to do this as well when I was learning this. I don't want you to forget that it's not just light rays going the way that we're studying. There are light rays all the heck over the place. You are attacked by billions of light rays coming from all different directions, and most of them don't happen to be entering your eyes. That's why if you're in your room with somebody else, that person can also see stuff. And you can talk about the same thing that you both see, because specular reflection isn't happening, it's diffuse reflection. You've got everybody able to see everything because light's going everywhere. It's just crazy. So, a mirror. There's the mirror, and Newton wants to see himself, so he looks into a mirror. That's the idea. Let's see. Oh, hi, Newton. Hi, me. And he's looking into the mirror, and he can see himself, so let's draw a little sketch of this. I'm going to say instead that Newton's actually going to be looking at a flower. So no, I like that for the rays. That's cool. My mirror will be sea foam green. Nasty. Here's the mirror. So the light's over here. There's gonna be a flower. Let's say I'll put the flower in a flower pot. Flower pot and flower. What do you want it to be? A pink flower? Yeah, this is just a pink flower. All right, and Newton wants to look at the flower. Newton had blue eyes, maybe, I don't know. What do you think? He had seafoam green eyes. Newton's over here. And he's all like, do I see a flower in that mirror? Maybe he does. Let's see. Okay. The only way that Newton could see a reflection of the flower in the mirror is if light came from the flower and hit his retina. So somehow there's a light over here. Wait a second. If this mirror is extending throughout all of space, it's actually going to be dark over here. And it's going to be light over on this side. So I'm going to say, maybe I should use, no, I could use blue. Okay, I'm gonna say that from the top of the flower, there's light coming off of the flower, and it's going to hit the mirror, and then it's going to bounce out at the eye, and it's gonna be like that. And our principal understanding of the law of reflections says that there is a dotted line here, dot, 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 and theta reflected is the same as theta incoming. The incoming angle is the same as the reflected angle, where the angle must be measured away from the normal direction to our reflecting surface. Okay, so that's fine, but the reason we don't see just a dot of light right there is because we actually see the flower. So that means there's light coming from this part of the flower also. No, wait, I think I mean there's light coming from this part of the flower. Let's say that that ray hit the bottom of our retina. There's a tiny, tiny different ray that goes just a little bit up, like this. And then it will actually hit the top of our retina, or our eyelid or something as I've drawn it. But notice that these rays are getting further apart from each other, at least they're supposed to. I think I automatically curved in because I didn't like it hitting my eyelash. But you have to imagine the eye's a little bit bigger. Step back, Newton, grow a bigger eye. Here you go. Newton's got a really big eye right now, and this makes a little bit more sense. So Newton's looking at the flower, and you see that these rays are diverging, so Newton says there's a flower there. But Newton says, wait, there's a flower wherever this light is coming from, because that's what you think. Light comes from a particular source. So let's draw a dotted line where this ray appears to originate. Are you ready? This ray appears to have come from inside here. We don't know where, but we're thinking somewhere back here was the source of this ray of light. That's what Newton's thinking, because he's looking in the mirror and he's seeing a flower there in the mirror. You know there's darkness over here. There's nothing here, but it says if that ray had come from there. And this ray, ooh, this ray looks like it came from here. Watch this. This ray looks like it came from right there. Whoa, sorry, we ended up curving a little bit. I'm going to do dotted lines whenever I'm in the darkness. This is the apparent path of the light rays that Newton sees. Okay, so they don't actually come from there, because they actually came from here and were reflected, but it's as if they came from over here. Let's consider another light ray that's actually happening over here. There's light coming out from the flower going this direction, and it bounces back. Let's see, it's going from the flower, and then it bounces back and goes directly back this way, and goes out that way. So that light ray, although Newton can't see that, it still might be useful for us to sketch it. That light ray seems to have come from right here. And we could do, what do you want to do, another one? Nah, let's not do another one. I'm saying that a lot of these light rays seem to have come from somewhere over here. In fact, oh, wait a second. It's as if, look where all these guys are supposed to intersect at the same point. It's as if there's a flower over here. And that's what Newton sees. He perceives the existence of a flower back behind the mirror. So can we define some stuff right here? I'm going to define this guy as the object, and this is the image. So the image is not real. There is nothing here. There's darkness over on this side. But I can define some other things. I can say that this distance right here between the object and my surface is the distance of the object between there and there. And this is the distance of the image. And what do you notice about the distance of the image and the distance of the object for a plane mirror? Well, personally, I'm noticing that they are exactly the same. All right, and we're going to call this guy, we could call this point P, and we'd in that case call this point P prime. And I can do more points, but it will make this much more cluttered. I decide to study just a certain point on the object and make all these connections like that. We're going to have so many more details when we get to curved things, mirrors and lenses. But I want to summarize what we're seeing right here. The image is upright. This image is upright just as that image is. Okay. Plane mirrors, let's see, upright image, but it's reversed left to right. You notice when you look into a mirror, and you're looking at your left side, it appears to be the right side if it were somebody else. You know what I mean? If you're looking at somebody else, you think that their right side is on your left side, but if you look at your left side in a mirror, it actually appears on the left side. So these guys are upright images, but reversed left to right. And another thing we can say about plane mirrors is that the distance of the image is the distance of the object. And also, we should say that the size, and I'm not going to give you a cool variable yet for size, but the size of the image is the same as the size of the object. Okay, so everything that we see in the mirror appears to be the same size. If it's a nice plain mirror, this nice very flat mirror is gonna give us the exact same thing. But look, oh, this is the size of the image, the same as the size of the object. No, it's a little bit smaller for a convex mirror. So we'll talk about those in greater detail. I think that's all I need to say about this. Is anything missing? Let me know if I need to add anything. I guess here's my fundamental point. My fundamental point is, it seems as if there's something here because these rays are diverging and your brain associates diverging rays with the presence of an object at a distance away from where the rays appear to originate. So at this location right here, your brain says there must be something there, because that's the only way I can get diverging rays that take up this much of my field of view. If there were actually an object here. You know, the bigger part of your brain, the more intellectual side of your brain says, I know there's nothing there. There's nothing behind that mirror. You can't go beneath the table and see the camera. I'm trying to grab it, but there's no camera beneath the table, even though I see a camera. There's a camera there. I'm gonna get it. Oh, I can't get it. And so, I mean, Lewis Carroll had some great things to say about this. You should read. Goodbye. Hi. Before we talk about mirrors, we need to talk a little bit about what it means to see things. But this guy right here, this is called a plane mirror because it's nice and flat, and we're gonna talk about them today. Yay, plane mirrors. This guy right here is convex because it doesn't look like a cave. It's like the other side of a cave, like you'd see from The Rock or something. You can use these often on cars to see an enormous range. See how you can see a whole bunch of my ceiling like that, and the camera. And this guy right here is a concave mirror because it looks like a cave. There's a little cavity inside of it, and you see how eventually we can get to a point where you're looking at the camera and you see it really big, and then upside down and right side up. Rays, now remember, rays come straight from the thing to your eye. Rays from this part of the flower are entering your eye. And if they're entering the lens of your eye, then I suppose some cool stuff is going on inside your eye that we'll talk about later in the retina, and you're getting some signal, and there's some lens action going on right here. Then you are able to see every bit of light that comes into the lens flower. And the flower, well, let's put the flower here first of all. What does this have to have? 7 or something if I'm doing this side? 4, 5, 6, 7. Prime numbers, flowers, yay. And the flower naturally sits in a flower pot. Here we go, and there's probably some dirt in there too. But if you see a flower, that means that, well, that's cool. So I don't know if you can see yourself now, but I hope that was interesting. But before we even talk about plane waves, we need to talk about what it means to see a thing. So let's say that I have a flower, and I want to look at the flower with my eye. I have the eye of physics here with some nice physics eyelashes, and I want to look over here at a flower.